Hi, welcome to Plasma Dynamics. This is part four of our SHP lecture series. My name is Jamie and I'll be presenting this lecture. So just a little bit about myself. I was born in Atlanta, grew up in California, went to Seattle, and now I'm in Columbia University just to show and highlight my journey. And it is frozen. Oh, it's not, just kidding. So I went to my undergrad. I did applied physics for my bachelor's at the University of Washington. And now I'm a third year PhD grad student at Columbia. So how I got into the fusion field was I volunteered at this lab called Hidasai at UW. I did an internship at SUI at D3D, which is one of America's few working tokamaks and national labs. And now I'm at Columbia doing my PhD. So sweet. So what do? I research disruptions within tokamak plasmas. So it's kind of difficult to contain our plasma sometimes. And a lot of times when we're trying to confine this plasma, you can have a sudden thermal loss. And this is called a thermal quench. And it's very difficult to model these kinds of disruptions. And they can happen due to a variety of different events that could cause these disruptions to occur. And knowing why and how they occur is really important. So learning how to model them is very important. So that's what I do. So in this example, you can see a typical disruption, sort of what it looks like. You have a sudden loss of thermal energy, followed by your loss in your plasma current. And then you can have things like runaway electrons, which are highly energetic electrons that are in your tokamak. And if they hit the wall, they can melt it, stuff like that. You can also have high forces that are imposed on your vacuum vessel due to things called like J cross B, which is your current crossed with your magnetic field, resulting in a force. So all these things are important and can cause trouble in tokamak plasmas. So this is just an example of all the different kinds of ways a disruption can happen. For example, you could have some maybe unidentified flying object that is present in your device, maybe a piece of metal, something that fell off, which could lead to some impurity in your plasma. Your plasma is no longer, just made up of deuterium, whatever. It could have some impurities, and that balance is very delicate. And if that happens, you could once again lead to high this, density products, and then it's yada, yada, yada. And it leads to almost the same result where you have a thermal quench and then leading to your current quench. So the end result always looks the same, but how you get there can be caused by a myriad of different ways. But that is a little advanced for where we're at right now. So let's just talk about plasmas. So first, we're going to do a quick review on the past SHP lectures that you've already covered. How does plasma physics relate to fusion energies? This is a concept that, you might not be super aware about. How is fusion and plasma related? Well, typically you should know that there are three typical states of matter. We talk about a solid. We heat it up a little, you can get a liquid. And then if you heat that up a little, you can get a gas. What happens if we heat up a gas? Well, that's what we call a plasma. So it's the fourth state of matter. So you can see that this gas, the molecules in the gas get so hot that the electrons can no longer just stick by that nucleus and orbit it. It actually, is energetic enough to move far away. But as it moves far away, there is an electromagnetic force, right? Positive and negative attract. So as it moves far and farther away, it suddenly wants to swoop back because it's attracted. So this plasma, sort of think about it as an electrically charged gas is a good way to think about it. In fusion, what is fusion? We joined two heavier nuclear atoms to form a heavier one. So typically you have a deuterium, right? One proton, one neutron with a tritium, one proton, two neutrons. We combine that together, you get a two proton, two neutron byproduct and a neutron that flies off, and you get energy. So this energy can be collected and converted into energy, but to do that, you need a very highly thermalized state. So you need a plasma essentially to get this reaction to even occur. So I talked about plasma, and we have been talking about plasma for the past few lectures, but what specifically is a plasma? I said it was a highly charged gas. So, what actually defines this? So we need to cover the characteristics of a plasma. So, like, what is a plasma, right? Like in this Pokemon. Well, a good quote from Professor Francis F. Chen, which is a writer of one of the introductory fusion textbooks that's really good, is plasmas are quasi-neutral gas of charged and neutral particles which exhibit collective behavior. So there are a few keywords here that's important. Quasi-neutral is one of them, and collective behavior is the other. So in neutral gases, right, regular gases, particles only interact through collisions. They don't really experience electromagnetic forces that I've talked about. Whereas in a plasma, they experience this collective behavior that is from electromagnetic reactions. So for example, if I provide an external charge in the plasma, all the particles in the plasma will simultaneously react. Whereas in a gas, maybe it'll just bounce around, something like that, right? So they react to an external stimuli simultaneously. This is what we call collective behavior. So looking at what is quasi-neutral. So say I had a plasma and it looked like this. It's in a big cloud, right? The, negative electrons can't go too far off from the ions, but they're not that close, right? You can see I have an equal number of positive ions and equal number of negative electrons. So from far away, when I zoom out, it looks neutral. But when I zoom up, I can see that it's clearly, there are parts that are more charged than others, right? Now, let's say I put a charge in it. When I put a charge, so you see 3 plus, instantaneously, the negative electrons will be attracted to that external charge. They'll be attracted towards it while these ions might move away a little. Typically in real life, the electrons, because they're lighter, will move the most. But as these electrons get close together, they'll start seeing each other, right? So then they will be repelled by each other. And then they will eventually realistically form this kind of circle where they are at enough of a distance to get as close as possible to the charge they want, but also they're repelled by their fellow charges that are nearby. So this is a sphere or a circle, and we call this radius the Debye length. This is an important parameter for categorizing a plasma. So the official definition of the Debye length is this equation that you see over there. The epsilon and the k, those are just constants, things we use for units. One thing that's just particularly that you need to know is that this Debye length is influenced by temperature on top and density and charge on the bottom. And that makes complete sense, right? These things influence how big this Debye length can be. You have plasmas that are on an interstellar level, they're massive, where you can also have a plasma in a fusion device that's only maybe a couple meters big, right? So definitely important. And the distance from the source charge at which you can't see the electric field anymore. So something important is that these positive charges over here can no longer see this 3 plus charge, right? To them, they see neutrality because these charges are canceling out this extra external charge that we're adding out. So in a way, it's like some kind of shielding effect. So there are 3 important criterions that Francis Chan uses to properly diagnose a plasma. So a plasma has to have a Debye length that is much smaller than the length of the plasma, or lambda d is much less than L, meaning that this Debye length can't be bigger than the size of your plasma. That makes sense. The number of particles that make up a Debye sphere must be more than 1. That makes sense, right? You can't just have 1 particle making up a Debye sphere. It's very many particles reacting and forming the sphere, an ergo collective behavior, right? All these charges moving together at once. And finally, the frequency of the charged particles and the neutral particles within the plasma are not that frequent, meaning electromagnetic motion dominates over regular collisional motion. That's important to know because there are many sort of things where you can see plasma physicists argue over stuff like, oh, is a fire a plasma? And in reality, this third criterion is really what sets apart, is a fire a plasma or not? It depends. Is the frequency of collisions of the charged particles and the neutral particles not that frequent? Is it more dominated by E&M reaction motion versus collisional motions? So that's what really sets apart like a fire from a plasma, right? So plasmas are used everywhere. So you can see right here, this is plasma arc welding. It's used to make planes and very important welding of materials. That's a plasma. The flame, like I mentioned, it can be a plasma. It could also just be a charged slightly ionized gas, and it's not actually a plasma. And then over here, you can see what a Debye sphere looks like in a more official drawing that doesn't look like the drawing I made. Perfect. So now, after talking about the criterions of a plasma, we're going to start about talking about single charge particle motion because plasmas are made of lots of large, small charged particles. So great. So just a review from last week, charged particles like to move along field lines, and we have this equation, F equals QV cross B. So just a quick quiz that I usually like to ask is, what was this motion called, and what does that X in that equation mean? We're not in lecture right now, so we're just gonna move on and know that this motion means gyro motion and the X means a cross product. And it moves in a helical-like shape around the B line. It sort of gyrates around, so your V is perpendicular to B, and remember your cross products are your result is a perpendicular component in both of the V and the B directions. So just to get a good visual, this is from NASA's simulators. They have a lot of cool videos called the Plasma Zoo that you can look on, and should be able to play. So you can, right, for the charged particles are dependent on their sign, on the direction. So you can see that these negative electrons rotate counterclockwise, remember, because they have a negative in front of their charge. So it's QV cross B, so Q, right? So it's negative, and the positives rotate clockwise, and they gyrate around this B field, which is this vector that's pointing outwards towards us. Now it's pointing up, and you can see that they follow along this field line, and they gyrate upwards in the same direction. So that's very cool, right? Interesting. So what is the frequency of its rotation? This is known as the plasma gyromotion, also known as the cyclotron frequency. Now, this is independent of the sign of Q, right? The sign of Q determines the direction of gyration, but again, you can have a negative frequency. That's strange. So you can see that it's dependent on your charge of a particle, the magnitude of the charge of the particle, right, times how strong your magnetic field line, and divided by the mass, right? Like heavier particles are going to gyrate a little slower compared to lighter particles. That makes sense. So usually I do a derivation, just an example of a proof. Proofs are really important in physics. Just learning to get familiar with that. I always highly recommend any sort of, physics laws or anything, seeing where it comes from is just incredibly important to understanding this. So I was going to do in this presentation, we do a derivation of the, I believe, the Larmor radius. So we're going to start. When you start a proof, you typically start with like a toy problem or a simple setup to your model. So starting from a system where we have zero electric field, we have B going into the page. So those X's mean going into the page, and if you have an O, you kind of go out of the page. So how I like to think about it is X marks the spot, so you dig in, and then O's are kind of like eyeballs that are looking out, so going towards you. So assume that you have a particle of charge Q and mass M, right? These are just variables that are just holding in place any certain values that are generalized. You have your magnetic field going into the page, like I mentioned. The particle is moving perpendicular to the magnetic field with velocity v perp. What is the radius of gyration? So a good way to start, you can pause this and try and tackle this problem yourself, but the good way to start is to remember your force equations. So what is a force? What is the force exerted on something that is rotating, and what is the force exerted on a charged particle? So for the second one, you should know that from last week on your previous SHP lecture, and the first one you might remember from a basics mechanics course. So how do we describe something for the force that's moving in a circle? What is that equation? So I'm just going to give it to you. This is the centripetal force formula, right? So F equals mv squared over r, where your v is perpendicular to your radius, and your force is pointing outwards, right? So you get that from that picture, right? Like that particle is orbiting around something, so it has some centripetal force. Where is that centripetal force coming from? Well, what's the other force that we have in this problem, right? What is the force experienced by the charged particle in an electric or magnetic field? So what is that? That is the Lorentz force, discovered by the guy right over here. So F is equal to QE plus R QV cross B. So you can already see our gyro motion is already included right over there, and we're just including this electric force that's right here. So this formula is important for forces experienced by charged particles. So if we pair this together, we can see we have two formulas, F equals QE plus QV cross B, and we also have F equals MV perp squared over R. Now, what are some assumptions that I can make based on how I set up the problem? Well, if you notice, we have zero electric field. So one thing that's really great is we need to simplify our problem statement. That makes things a lot easier for derivations, and it's always good to reference back to what your toy problem is really saying, right? So here we have zero electric field, so we can cross out that E. So we're left with F equals QV cross B, or the cyclotron motion force that I was describing earlier. We can now set, the cross product, right? So for cross products, it's a little difficult, especially if your V is not exactly perpendicular. But because we know that in our problem statement that I gave you, V is perpendicular to B. So for the cross product, we just multiply the two together. So you get QV perp times B. It's just the magnitudes. So cross products, think about things in perpendicular directions. So now we have F equals QV times B. We can now look at our first equation instead, because we've simplified our second equation. Remember that we are trying to solve for R. We're trying to find the radius of gyromotion. Well, I know F equals QV times B, and I know F is equal to MV perp squared over R. What do? We can get rid of F, right? We can set them equal to each other. A good way this problem is also very reminiscent of these tetherball problems that if you've ever done in a mechanics course, very similar, like the tension of the cable versus the motion of the spinning. It's very similar. It's like the tension pulled by the electromagnetic forces over the spinning, right? So you set them equal to each other and solve for R. So typically I do this on the board to show you. I'll leave it as an exercise to the watchers to do themselves. So what do we get? This is called the Larmor radius or the gyro radius, and it's V perp divided by R Larmor frequency, or if you had solved it the way that I had shown you, it's MV over QB. Something important is that the sign of Q determines the direction of gyration, but your radius can't be negative. You can't have negative distance. That would be strange. So it's always greater than 0. So we take the magnitude of that, right? So this is called the Larmor radius. And it's a very important concept that we're going to cover in this next portion of this presentation. All right. So we're now going to get into the next portion of the presentation where we're going to be talking about something called drifts. And something I want you to think about when we're thinking about drifts or what drifts even are is in all these example problems that I've talked about so far, our magnetic field is the same strength everywhere. But what happens if the magnetic field is not the same strength everywhere, right? So we're going to go to the next, right? So here is an example. This is more similar to real life, right? So here on top, you have a magnetic fields that are more closer together. Remember, when we draw things closer together, it means that it has higher field strength versus more farther apart, it's weaker. So top, we have stronger magnetic fields, and on the bottom, we have weaker magnetic fields. And say I have some particle, a positive particle, just floating in between with some initial velocity going up, right? And some particles will naturally just move a little Brownian motion, so that's where that initial velocity comes from. So as I go up, right, I am orbiting around, remember, they will orbit around these magnetic field lines, right, and they have this Larmor radius RL. So if we remember this formula, MV perp over QB, what is at the bottom over here? It's B, right? B is at the bottom. So my Larmor radius is going to be a little shorter in comparison to if once I move over here and I go into my weaker B section, right? My B in this formula is decreasing. So the Larmor radius will, if something is decreasing at the bottom of a fraction, what happens to the thing, the actual thing? It gets bigger, right? 1/3 is bigger than 1/4. So you can see my Larmor radius has now increased in size over there. It's a lot bigger. So now, next step in time, I'm over here, right? But I'm no longer back at my initial point where I started with. I had moved a slight distance. I moved a slight distance, delta x, and then I start the process all over again. I rotate a little, my Larmor radius is small, and then I rotate a big amount because my Larmor radius is bigger because of my magnetic field. And over time, you can see that I have moved by 4 times delta x, right? The particle is drifting to the left naturally, just because my Larmor radius is changing slightly, because the magnetic field is not uniform as it is crossing into different field strengths. Does that make sense? Okay. So now this is called a drift. So what is a particle drift? Well, the particle is moving with a constant distance, delta x, and in this case, it's to the left every orbit. Every orbit takes place in the same amount of time. This is the cyclotron frequency that I was speaking about. And if we can call this delta t, which we can describe as QB over M, right? And that in that section is constant, right? Delta x over delta t is constant, right? Your time, every orbit is taking place in the same amount of time. So because delta x over delta t is constant, which if you know from a mechanic class, that also means your velocity is constant. Velocity is delta, the change in distance over the change in time. So the velocity is constant, therefore there's no acceleration. So the particle is just drifting. It's at, there's no acceleration. It's not purposefully moving to the left in any like driving work being applied, right? It's just naturally just going like this, just slowly across the screen. I like to think of it like an astronaut drifting in space, even though the astronaut is not maybe doing anything to particularly move. It's just natural Okay, so what if the particle is negatively charged? Is this different? Well, I'm going to go in the different direction because the direction of gyration is reversed. It's counterclockwise, right? But I'm still experiencing the same effect by this Larmor radius that's here. So I'm moving into a stronger B area. Therefore, my Larmor radius is going to be smaller. Then I drift down. Then I gyrate downwards into a lower magnetic field section, and my Larmor radius is bigger. Sorry, before I said the Larmor radius is smaller, yes, and then I go to a weaker B field, which means my Larmor radius is bigger. Fractions are sometimes confusing like that. But you can see I slowly drift just a little bit, and I'm no longer at my original starting position. So it drifts in comparison to the positive charge in the opposite direction. So what if my B field is no longer just in this problem, like suddenly strong magnitude and then suddenly like very weak? It's usually like a gradient of some kind. So it's basically the same effect, but your Larmor radius is changing continuously. So the path shape is slightly different. And the shape of this path is called a cycloid. So I have a video. Oh, sorry. So something important to note is this math concept called a gradient. So a gradient is how do we describe fields where strength is changing throughout space? I like to think about gradient as more like a slope because it is very similar to a slope. It points in the direction of increasing field strength, just like if a slope could have a direction, essentially. So you can see in this direction, it points from weaker to stronger. So my grad B points up, right? So here I have some examples of grad B. So where would grad B point in the black dots? Remember, grad B is an arrow that points from that points from weaker to stronger field lines, like a slope, very similar to that. So in that black line, where would it point? In the first black dot here, it would point inward, right? In this example, at this black dot, there are less field lines here, more field lines over there, it would point inward. And since this is all uniform, right, all the fields are equally spaced, there's no change in this density, right? It's 0, right? So over here, what direction would it point? This way, right? What direction would this point? This way, right? It points from less cluster to more cluster, less strong to more strong. It points less tacos to more tacos. It points like that. You know what I mean? Hopefully that makes sense. So in a 3D effect, this is what it would typically look like. Like on a 3D, say I had a hill or something, it would be like pointing upwards like that, like a slope, very similar to that. So this is called what I was talking about earlier, where there's a drift due to your change in magnetic field strength. That's called a grad B drift. And this appears when B is non-uniform in space, meaning in certain areas of space, your magnetic field is stronger, and in other points of space, your magnetic field is weaker. And then because it modifies the Larmor radius, because the Larmor radius is affected by B, it will naturally drift. And the equation for the velocity of the drift is right over here. It's very complicated, but all you need to remember is that effect that I just described earlier with a bunch of slides. This equation is just describing that in math language, right? And so you can imagine that this happens a lot, right? Like this is very similar to Earth's magnetic fields. So, you can imagine if this was a sun, a charged particle coming in from the sun, they will naturally have a grad B drift. So this happens a lot. You're never going to have, most of the time, you're not going to have something that is this situation. Okay, so here is a video that will explain more. Will not explain more, but it's a good visualization. You can see B is increasing in strength as I'm going up in this direction. And then you can see as these particles are rotating around, no longer are they staying in place anymore. They're drifting slowly in opposite directions. And that's due to the fact that they are gyrating in opposite directions. So they drift in opposite directions for a grad B drift. So you can see, la 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 la, it's rotating away. I hope this visual is important. You can stare at it some more. It's the Plasma Zoo library on NASA. So it's very cool. Hopefully it still exists. If not, I'm sorry. Okay, so summary of the grad B drift. Basically, it occurs when magnetic field strength B is not uniform throughout space, which is very common. It's due to a changing Larmor radius over the course of the particle's orbit, because the Larmor radius is affected by B. So higher B's mean tighter Larmor radiuses. Lower B's mean not as tight Larmor radiuses, right? Which changes the course of the particle's orbits. The positive and negatively charged particles drift in opposite directions because they orbit in different directions when they are gyrating around a B field line. And we use the gradient or the grad operator of the magnetic field to describe the direction in which B increases more strongly. Meaning if I had weaker magnetic field lines over here and stronger magnetic field lines over here, my grad B direction would point in that direction. So hope that was helpful. Particles drift perpendicular both to B and grad B. That makes sense based on the illustration that I showed. So now we've discussed just a basic drift. We are going to move on to why do drifts happen. So drifts occur from changes or deformities to the Larmor radius over time. So they can occur if B is not uniform in space, right? That leads to the grad B drift. But what happens if I introduce things like an electric field? What happens if my fields are curved? What about forces like gravity? These are all things that can affect the Larmor radius and therefore change or can introduce particle drifts. So what happens if I introduce an electric field? A lot of times you'll have an electric field along with a B field. If you're familiar with a lot of electromagnetism problems, you know they tend to be very well coupled together. So what happens? Well, let's look at the Lorentz force formula. So given a uniform E field and a B field, we get the E cross B drift. And we can see this from the Lorentz force, right? So over here you have QV cross B. That's the gyro motion that I explained before. This defines this Larmor radius that I explained that we derived earlier. But we also have QE now, which creates a force along the electric field. So force meaning acceleration, and acceleration meaning a change in velocity. It's going to eventually affect our velocity in some way. So let's look at this problem. So I have B fields, which are these little eyeball-looking creatures, and they are pointing outwards. Remember, if they look like an eyeball, it's looking out at you. And I have an E field that is pointing upwards. It is uniform in space. And then remember our Larmor radius formula and our force formula, which is F equals ma, the change in velocity over the change in time, but we can also represent it as QV plus QV cross B as Lorentz force. So first question, in which direction is the electric force on the particle, right? So our particle is positive, right? So force that is the electric force is QE. So since Q is positive, it's just Q, and then times E, which is going to be in the direction of E, right? So your F is going to point parallel in the same direction as E. So as long as the particle is moving upwards, its speed is going to increase because that force is pushing up on that particle, right? If I'm moving downwards, it's going to be in the opposite direction of my force, so my velocity will decrease. So we know that the particle will start to gyrate due to this B field, that QV cross B. It's going to gyrate around this field line. So what happens when I'm gyrating along the field line? What happens to my particle's speed? Or in other words, where is the particle's speed maximized as of being affected by QE? So when I'm moving from here to the top of this if I'm orbiting around this particular eyeball, if I'm moving upwards to the top, I'm now at the maximum point. Here, as I'm moving up, I'm moving in the same direction as my electric field force. So my initial velocity is adding a sort of delta V of the force being pushed up by the electric field. So my V has increased. So what happens to my Larmor radius? Right? My V is increasing, so my Larmor radius is also increasing. So my Larmor radius has increased slightly. But let's say I move downwards now because I'm gyrating along the field lines. I have to move in around this magnetic field line. As I'm moving downwards, the velocity is now in the opposite direction of the force. So that means that force is now combating against the velocity, so I'm going to be slowing down, which means my perpendicular velocity is decreasing. If my perpendicular velocity is decreasing, what happens to my Larmor radius? It also decreases. So now you can see the particle has slowed down, so the speed is now the same as it was in the start, but the particle is moving downwards. So because I'm here, over here. So the radius is now at the beginning. It no longer has that added component. And so here at the bottom of this particle's orbit, as I was saying before, right, I'm going in the opposite direction. I'm moving downwards in comparison to the force. So my speed is now being minused by the force. It's slowing down, right? So now my Larmor radius has decreased by some amount, represented by this arrow being smaller. And so when I return back to my original position, I am not at my original position anymore because my Larmor radius has decreased. So you can see I have moved by some amount called delta x. So because the Larmor radius is bigger in the top half, and that's because I'm in the same direction as my E field, then the bottom half of my orbit, which is in the opposite direction of my force caused by my E field, this causes the Larmor radius to change, which causes a drift in the delta x direction. It has shifted to the right slightly. This movement has drifted over slightly. So I hope that was slightly clear. Basically, this is a very similar effect, causes the grad B drift, right? Like my Larmor radius is just being changed slightly by my system, and it's no inherent sort of, rocket attached to my particle. It's just the outside factors affecting my Larmor radius, which is down here. But instead of my B being affected, it is now my perpendicular velocity being affected. But this movement to the right is still with a constant velocity, so this movement itself doesn't have acceleration, right? This drift is still considered a drift, right? So this drift is called the E cross B drift. It's the direction of the drift given by the cross products of the E and B field. It's going in the E cross B direction. So something familiar is the right-hand rule, so you can check this really quick. So my E field is up, my B field is out of the page, and for a positive one, my thumb would be pointing in the, it's mirrored here. It'll be pointing in the, for you guys, this direction. Nope, this direction. Sorry, it's mirrored. So you can see it's very easy to check. So what happens when we introduce a different force? This would be the exact same effect. So in this situation, if I had gravity going upwards for some reason, it would do the same thing. So that's just called an F cross B force. So what would happen if the charge was negative? Well, it would actually have the very similar effect, the same effect, because like a grad B drift, the negative charge goes in the opposite direction, orbiting around the magnetic field line, so it will drift in the opposite direction. So in the negative F cross B direction, right? So instead of pointing upwards, you can point downwards and out of the page, and then like this direction. The cross product rule is hard to show over Zoom. So this is the general expression for the velocity of the drift. So it's F cross B divided by QB squared. You can also do this derivation if you want, but it is not trivial to show. So we'll just explain it through this conceptual way here. So notice that the drift velocity depends on the magnitude and sign of the particle QB that's in the bottom of this fraction. So what is the expression of F cross B force due to gravity? So what is the force due to gravity? We just plug in mg, because the force of gravity is equal to mass times gravitational constant. So here, that's just demonstrating that you just plug in mg into your F. And so this is the gravitational drift right up there. And so particles that are drifting in our atmosphere, charged particles drifting in our atmosphere can experience this gravitational drift. So what would be the expression for the E cross B drift, right? So what is the force due to the electric field? Well, we remember from Lorenz's formula that the force due to an electric field is QE. So we put QE inside of that F. Because it's QE inside of the F and there's a Q on the bottom, the Q's cancel out. So you end up with E cross B divided by B squared. So what does that mean? It means that the E cross B drift velocity is in the same direction for positive and negative charges. So even though they gyrate in different directions, they drift in the same direction. So mathematically, we can see it's because these Q's cancel out. So here's a video that can be helpful to visualize the E cross B drift in a better way. So you can see that even though they gyrate in the opposite direction, they still drift in the same direction. So your B is pointing outwards, your E is pointing up. If you want to use your right-hand rule, you can easily see that it will go in that direction. again, it is hard to visualize on Zoom. I usually put the index finger, the pointer finger in the first direction of the first term, cross, and my middle finger in the direction that is the second term, so B, and then my thumb would point in the direction of the result. I think other teachers have other methods of doing the cross product, but I use a very traditional right-hand rule. The summary of the F cross B, the generalized force drift. Particles subject to a perpendicular force in a magnetic field will drift with a constant speed in a direction perpendicular to both F and B. And depending on how F is written, you can either be charge dependent or non-charge dependent, right? So this helpful image on the right-hand side shows that on the very top-hand side, you see that the charged particles orbit in different directions, but with an E force, they drift in the same direction, but with like a generalized force, like let's say gravity, they would drift in opposite directions. And that's just due to the fact the force due to an electric field has a Q inside of it, and the charges will cancel out. So I promise this is the last one. This one is in my opinion, one of the ugliest ones. What happens if my field lines are curved, my magnetic field lines are curved, which is very common. You can derive it from the generalized force drift. It's basically the force of a centrifugal force, which many argue is not a real force, but it depends on your frame of reference in reality. So you can derive it, but it's very ugly. So just to note that you'll experience some kind of drift due to the curvature of your field line. So in this picture, you can see that my field line is curved here and it's gyrating around the field line. And due to the curvature, there's a drift that's drifting into and out of the page. It's not drifting upwards. But you know that because it's a cross product, right? It's the radius of curvature, and that's just like a radial vector that's pointing from, like, all curvatures can be represented as like a circle, right? So like from the center of that circle outwards towards that curve, it's like our radius, it's that direction, radius pointing to the curvature, and then the direction of B, the cross product of that. So in this case, it's kind of like this, and it would be moving outwards. It has to be perpendicular to both. So again, you can also use the right-hand rule for that. So R would be this finger, B would be this finger, and it would be pointing in and out like that. So very cool. This one is also charge dependent. If you look here, there's a Q at the bottom. And again, you can derive this from the generalized drift force equation. So that was a lot. Sorry if I went a little fast, but why does this matter in plasma physics at all? Well, it's very kind of the fundamentals, right? Drifts are present in a lot of times. Like what drifts would be present in this picture, assuming no electric field? You do have gravity though, right? You have curves, you have gradients, right? Like the gradient, fun fact, what direction would the gradient point, right? You have less stronger field lines here compared to inward. The gradient would point inwards like that. Just a review of the gradient vector, right? You have curves, you have gravity. So all these things will introduce drifts. So your single charge particle motion is actually pretty complex, given all these drifts that you have to take into account. So, right, so you have, like I mentioned, you have gyro motion, right? It's gyrating around these field lines. You have a bounce motion, it's going up and down. You have drift motion. And the bounce motion is due to this thing, there's like a mirror effect, right? It's bouncing along up and down these field lines. Cool. So very complicated. That single charge particle motion can be this complicated. And if you think about it, sort of what's a real life example, right? The aurora borealis is a great example, right? I was giving you an Earth picture. Well, where do charged particles come into this picture? Well, the sun vomits out a lot of charged particles in its solar wind. They end up drifting along these field lines and eventually going to the poles where they collide with the particles in our atmosphere, which creates light emission, and then they create very pretty pictures for us to look at. Or I guess pictures, I guess objects to look at, effects. I go outside. So just a quick summary of what we've covered so far. We covered what makes plasma plasma versus just a very hot gas. We covered the Lorentz force and gyro motion. We derived how to get the radius of gyration, which is called the Larmor radius. We talked about single particle motion, especially drifts. We talked about the four general drifts that we tend to look at, which is the grad B drift, the E cross B drift, generalized force drift, and the curvature drift. They are complicated, but, believe in yourself. They all are due to the effects on the Larmor radius. And we applied how single particle motion applies to a real-life example of the aurora borealis. So normally I would ask any questions so far, but you can't talk back to me. So normally we're going to go on a break time. You can pause the video and get a snack, but for now we're going to keep going. How do we quantitatively describe plasmas? So we talked about single charge particle motions. How does that relate to plasmas? Well, plasmas are made up of many charged particles, and you can imagine that it gets a little complex. So something important to cover is the idea of fluids. So fluids are liquids or gases or plasmas that may continuously move and deform by a force. It's just a way of thinking about, a lot of particles at once. So instead of tracking every single particle, right, like how annoying it is, like to do every single particle in that motion, we instead break up this fluid into bigger sort of volume element chunks. So it's called a fluid element, as you can see here. And so this chunk of particles is now moving along with its flow, right? Instead of tracking a single particle, we track a chunk. So we can then learn about things like how fast are these chunks moving? That's velocity. How are these chunks squished or stretched? Right? That would be pressure and density. How do they interact with each other? Forces. And what happens over time? Fluid evolution. So it's a lot simpler of a way to learn about some kind of fluid. Instead of tracking every particle in the fluid, we can track these chunks of fluid. And that's more of like a fluid model, fluid perspective. So it's called fluid mechanics. And it's used everywhere. It's not just used in plasma physics. Weather. So how do you predict hurricanes and stuff? That's fluid mechanics. Ocean currents, aerospace. A lot of aerospace stuff is a lot of fluid mechanics. Even in medical, right? You can see like cardiology also uses fluid mechanics, which is pretty cool. And if you're an F1 head, this is fluid analysis, right? So how all fluid mechanics is a very important part of science and how just a very good framework in studying fluids. So how do we do this in plasma physics? Well, in plasma physics, we combine fluid equations with ENF. We merge these two together to create our framework, our plasma physics framework. Since our fluid elements are full of charged particles, they can experience ENM effects, so we have to include those. And we don't want to do just little single particles, we want to do these chunks that I was mentioning. So it's very convenient. Great, so what do we do with this? How do we describe a plasma? Well, going from most simple models to most complicated models, right? And what I mean by how do we describe a plasma, I want to learn different things about the plasma. How fast is this plasma moving? What is it going to behave in, let's say, 20 seconds? What does it do? Right? Given this system, how does it react? Right? So these are all the reasons why we make a model, which is just a set of mathematical equations that will predict its behavior. And they can be as most complicated as you want to least complicated as you want, right? So in this first sort of model that we tend to use is called single fluid MHD, and it's where we approximate the plasma as one giant fluid. So it's very simple. It's not that detailed, right? Because, you're just approximating the plasma as one big fluid. So you don't really need to take into consideration individual particles. You can treat it with little fluid elements. So in this analogy, I like to say it's like one big river, and we use this equation on one big river. It was founded or forwarded by this guy, Hans Alfvén, which is over there. Very cool. So it's just using fluid mechanics on the plasma as a whole. So then we also have the two fluid model, which is a little more complicated because instead of using one fluid, just describing the plasma as one fluid, we describe the plasma as two fluids. So one fluid is the positive charges and the other fluid is the negative charges. So this is a little more complicated because you have to consider two different fluid streams. And so you have a set of equations for both of them. So your number of equations will increase in this model. So it's more complicated, but it is more detailed, right? Because they will be moving in opposite directions because they have different charges. And the final one is something called kinetic theory. So this is very high fidelity and it's very complicated. There are very few cases you can actually solve by hand. But instead of using a fluid model where we approximate our plasma into chunks of particles, we instead, like I said, do every single particle and we have a model for that, right? Like I'm tracking every single particle. That's very complicated because a plasma can have many particles. So going into detail for each one, right? Single fluid MHD, we describe the plasma as one big cohesive fluid. So like in this river analogy. We will use typically two equations to help us capture the dynamics of the plasma in single fluid MHD. Their names are the momentum equation and the continuity equation. Again, you don't really need to know them in detail unless you really want to be a plasma physicist. So the momentum equation, just to go over what they are, the momentum equation is literally just F equals ma, but for a fluid chunk. So in this case, we just sum up all the forces present in our system, right? So there's electromagnetic forces, right? Because we're dealing with electromagnetism. So you have Lorenz's force, you have collisions. Let's say the plasma, the particles inside are bumbling into each other, right? So you can also have things like pressure, right? Because we're treating it like a fluid system. So again, you'll have something like pressure, maybe you have gravity, et cetera, et cetera. And oftentimes we actually don't consider collisions. Normally we assume it's collisionless, just for simplicity. But other times you will assume collisions. This is just depending on how complex you want to make your system and how accurate you want your model to be, right? Sometimes you don't need very accurate things. If you want some generalized, what is the general temperature of my plasma? You can, use something like a very simple model. So the continuity equation is just an equation that describes the flow of a fluid. So if you're familiar with fluid mechanics, maybe this picture seems relevant to you, right? So what stays inside is basically what goes in minus what goes out, right? In my system, what stays inside this, let's say, chunk equals what goes into my chunk and what goes out of my chunk. If there's nothing getting stuck, then what goes in equals what goes out. This might seem very simple in words, but in math, it looks a little confusing, so I tend to say it in words first. And those two equations can help us solve for a myriad of different things that you would like to solve for, like pressure, etc. So now going over what two fluid is, it's basically the same thing, but we treat two separate fluids, electrons and ions. So we basically use the MHD equations, but instead of just having two equations, we have four, because two of them are for the ion and two of them are for the electrons. So in a total, we would have four equations to solve our system with. So this is the momenta equation for the two fluid equation. You can see this is the Lorentz force. You have pressure, you have any other forces, and you have collisions. And instead, you would just replace this with like the charge of the ions, the velocity of the ions, or you could be the charge of the electrons, the velocity of the electrons, etc. So you would have four equations, and then you do the same for the continuity. What's the velocity of my electrons versus the velocity of my ions? Because you're treating them as two separate fluids, and they can move in different speeds, or they could have different charges, right? So yeah, and the final one is kinetic theory. Instead of treating the plasma like a fluid, we look at each individual particle and we add up those quantities in their respective space. So if any of you guys are familiar with like in high school or whatever, you'd be like, what's the curve like? What's the distribution? This is exactly what we do. I saw, like, for example, just explaining distribution functions. If you had a bunch of students taking a test and then I graphed and plotted everyone's results and I get a little bit like a bell curve, right? A distribution of the grades that every student gets. So for the kinetic theory, I literally do the same thing. I sum up all the velocities of the particles and I can get a distribution of the velocities of the particles. So that's just a way that you can keep track of all these single particles a lot better. And then you manipulate these distribution functions to figure out what you want. So like temperature or stuff like that. So how do we pick which model to use? There's three main models in plasma physics. Which one is best for my situation, right? So when I want something simple, when I'm looking at overall movement at large spatial scales, like in a tokamak or a solar corona, and you need to care about quantities like pressure or density, those don't need to be as in-depth or in detail with a model that is high fidelity. So you can use a simple model like single fluid. If you want to care more about particle interactions, the interactions between electrons and ions, but we aren't too microscopic, right? Looking at electron interactions, things like waves or where ions and electrons would behave differently. So in this case, we would use the two fluid model. And finally, for kinetic theory, when particles are too sparse to be treated like a fluid, so think like really far apart plasmas where you have a particle and like 10 meters another particle. You can't really approximate that as a fluid because fluids are like, I'm treating chunks of particles. But if they're really far apart, then you can't really have a chunk of particles. You would have a particle. So you would need to use something like kinetic theory, which is more about single particle motion and just adding all of those quantities up. So you know, think like space plasmas. You would use those for. So this is just a very quick overview of 3 different methods we look at plasma physics with. So just a summary of what we've covered so far. I know we've covered a lot of ground. What makes a plasma versus just a gas? That is determined by things like the Debye. We derive the radius of gyro motion, or the Larmor radius. We had single particle motion, grad B, E cross B, generalized forced, and curvature drifts. So those are the main drifts that are present in single charge particle motion when we think about plasma physics. We talked about the aurora borealis. We talked about what a fluid picture or a fluid perspective on physics kind of looks like, how fluids and plasmas are similar, and then the 3 different ways we analyzed plasma behavior, just learning to model plasmas, MHD, 2-fluid, or kinetic theory. And then we talked about which method is best for different applications. So I'd normally ask any questions, but you can't talk back. So comment questions. This is also one of the hardest classes this is one of the hardest sections in the course. So congratulations if you've made it this far. And so again, here's the plasma movement simulations that I used in this presentation, Plasma Zoo. There's also the Princeton Plasma Physics interactive resources. They're really fun. You can construct your own tokamak and like pretend that you're a power plant. You can also like remotely connect and turn on their experimental devices, which is kind of interesting. You do have to queue up for that. And if you want a really good, so where I got this presentation, how I made it, you know, these are really good deep dive textbooks. If you love textbooks, to look into more. I recommend the Francis F. Chen one for basics, and then the one by Fradberg is if you have a little more experience, especially if you're familiar, really comfortable with E&M, and if you already read Francis Chen's textbook, Fradberg is a good next step, or you could read them in tandem. So yeah. Sorry if I went a little fast. Hopefully you got something out of this.